So now let's use this formula that we just derived for logistic growth to talk about long-term population for some sort of town. So let's look at, let's actually just do world population. And what I want to do is I want to look at the following data points. So we know that in 1999, the world population, was 6 billion. And in 2011, the world population was 7 billion. Okay, so assuming logistic growth, and that's a big assumption, but this is one model that you can come up with to describe the data and see how well the model fits. But assuming logistic growth, I can't write, can't spell. I mean, so assuming logistic growth. So assuming logistic growth and assuming that the maximum, so assuming that the max population is say 12 billion. Estimates differ on that, but 12 billion seems a safe, nice round number. So let's assume that the maximum population is 12 billion. What I want to know is when will the population reach 11 billion? So when will the population reach 11 billion? Okay, and so that's what we want to know. And we've already derived the formula, so we might as well just use it at this point. That P of t is MC. M is 12, so 12c over e to the minus mkt, so 12kt plus c. And what I want to do here is let's let t be in years. And t equals 0 is going to be, let's say it this way, t is going to be the number of years after 1999. So in other words, t equals 0 will be 99. In 2011, we had, that was p of 12, because that was 12 years later. And so let's let t be the number of years after 1999. And then we know that our initial population, so we know that p of 0 was 6. So 6 billion. Okay, here I should just mention, I should say this, p is in billions. Okay, so p is in billions. So 6 is p of 0. And then if we plug that in, let's see, we're going to end up with what? We're going to end up with 12c over 1 plus c. And that means that c has to be 1. Okay, so if we solve this for c, we'll end up with 6 plus 6c is equal to 12c. Yeah, so c is 1. So c is 1. So that means that our population is going to end up being 12 over e to the minus 12kt plus 1. And then finally, to find k, we use our second data point. We know that p of 12, in other words, the population in 2011 was 7 billion. And that's 12 over e to the negative 12kt. So it's another 12 plus 1. And so let's see here. This is going to be, now we just need to solve this for k. So what we're going to do is we're going to take, we're just going to simplify. We're going to have 7 twelfths is equal to 1 over e to the negative 144k plus 1. That means that 12 sevenths is e to the negative 144k plus 1. And therefore, e to the negative 144k is equal to 5 sevenths. Take a natural log of both sides. K is going to be the natural log of 5 sevenths divided by negative 144. And then that works out to be, so that works out to be 0.00234. Okay, so that is what that turns out to be. Okay, so that's fine. So that's our k, and therefore that means that we finally have our function p that we're using as our model. So p was, I need to go back up and rewrite it, but this is 12 over e to the negative 12k. So this is 12 times 0.00234 t plus 1. And then finally, we need to solve when p of t is equal to 11. So we're going to solve that equation. And then to do that, we're going to have 11 is 12 over this mess. So negative 12 times 0.00234. Okay. I want to make sure that I'm doing this right here. Yeah, so everything's fine. So t plus 1. Okay, so we're going to solve that for t. And then we'll just do the usual algebra, divide both sides by 12, take a reciprocal, take logs, subtract 1, divide by the stuff in front. I'll leave it to you to check out the details. You can definitely do this. But we end up with t is the natural log of 11/12 over the natural log of 11 over this quantity. So we end up with, I'll just leave it to you to check that we end up with t is 85.52. So that means that somewhere around between 2084 and 2085. Okay, so around June 2084, according to this model, the population will reach 11 billion.